Now that we understand what the serial interval is, I want to explain how it can be estimated in practice. And when I say estimate the serial interval, what I really mean is estimate the serial interval distribution, because the serial interval varies between individuals and over time, and so there's no single one number that describes it. It's a distribution over possible serial interval values. And the method I present in this video is going to be based on the analysis that was done by Nishiyura et al., and I'm going to put a link down at the bottom of the video to this, which was a study that was done towards the beginning of the Covid-19 pandemic and enabled some quick but very useful estimates of the serial interval for the disease to be determined. So let's just remind ourselves what the serial interval is. The serial interval is the amount of time that elapses between symptom onset in a first individual and symptom onset in a second individual where the first individual has infected the second one. So unsurprisingly, to be able to estimate the serial interval, what we need is a bunch of pairs of individuals where we think that individual A infected individual B. And what we also need is the time when symptoms occurred in individual A and they occurred in individual B. And so this might be, for example, the 17th of Jan 2020 for individual 1, and then the 20th of January 2020 for the individual whom they infected. And then we'd have another row for a second individual that might be again, let's say the 17th of Jan 2020, and then symptom onset for the second individual might have been the 19th of Jan 2020. So we can imagine that we have lots and lots of possible pairs of individuals. Then what we could do is we could draw a graph of this. So we could imagine that we've got lots of individuals and we draw a histogram of all the potential time differences between the onset of symptoms in individual A and individual B. So here we'd be plotting TB minus TA effectively. And our histogram might look something like this. So imagine we've got some data that looks something like this. And the basic idea with trying to estimate a serial interval distribution is that you would fit some sort of probability density to this curve. So we might fit a curve that, let's say, is a gamma distribution. But lots of other possible distributions are also feasible here. And by fitting a probability distribution to these data, effectively that probability distribution then acts as our kind of serial interval distribution. So that's the basics of how you estimate a serial interval, but there are some complexities. One is that we have various uncertainties. We have the uncertainty in the actual links. In other words, is it actually the case that this individual whose symptom onset occurred at this time actually infected this individual whose symptoms occurred on the 20th? So typically what happens when you record these data is that individuals record whether or not it is sort of very likely, in other words, a sort of confirmed link, or it's just probable that there is a link there. So various methods for estimating the serial interval distribution can actually take into account this uncertainty in the actual links themselves. There's also an uncertainty in the actual timing of symptom onset, because people's recall isn't necessarily perfect, so they might just know that symptoms started to occur between a certain time point and a sort of later time point. So some methods try to take into account the uncertainty in the timing of the symptom onset. There's also a subtle way in which the naive approach that I've described thus far can go wrong. So imagine that we've got an individual who is infectious and they go on and they infect a certain person at a given time point and who later has symptoms, and then they go on to infect a bunch of other individuals at future time points. Now, if we are sampling at the beginning of an epidemic, it is possible that what we're actually doing is we are truncating this distribution, because we are just sampling before we have had time to see all the people that that individual has actually subsequently infected. And so if we didn't account for this truncation in some way, then we might be artificially reducing the length of the serial interval distribution. And so there are various methods to account for this sort of truncation that occurs during the sort of early stage of the epidemic. So there's this sort of early stage truncation that can occur, and statistical methods exist for accounting for that early stage truncation in the serial interval distribution. So in summary, to estimate the serial interval, we need pairs of individuals where we have some degree of certainty that individual A infected individual B, and we have some degree of certainty as to when their symptom onset occurs. If we have a bunch of these different individuals, we can then draw a kind of histogram of all the potential serial interval values, and then we can try and fit some type of probability distribution to that. But there are various complexities that we sometimes need to be aware of, some uncertainties, particularly in uncertainties in the links between individuals and uncertainty in the timing of symptom onset. And also we have to be aware, if we are doing this sampling at the beginning of an epidemic, we might actually be artificially truncating the serial interval distribution.